In this video, I'll show you how to determine the reaction order. How do we determine the order of a reaction? It's very simple for elementary reactions. When you have an elementary reaction, you just need to look at the coefficients of the reactants. These coefficients are the reaction orders with respect to the corresponding reactants. So if you see this elementary reaction, you go from 2A plus B, you get products. Well, this is a second order with respect to A and first order with respect to B. Overall, it's a third order reaction. Very simple. But what is an elementary reaction? An elementary reaction is a single step reaction. And if you see coefficients in front of those reactants, these coefficients tell you exactly how many such reactant particles are involved in the reaction. So if you see 2A plus B in an elementary reaction, you know in this reaction, 2 A molecules and 1 B molecule must collide with each other at the same site with the right orientation. And overall, these 3 molecules have enough energy to overcome the reaction barrier. All right? Let me give you more examples. Assuming this A2 products is also an elementary reaction, and then we know it's first order with respect to A, and also the overall order is 1. What about A plus B here? Well, it's first order with respect to A, first order with respect to B, and overall it's second order. What about this one? It's second order with respect to A, and overall it's a second order. What about this one? We talked about it over here, but we swapped the coefficients here. Well, that means it's first order with respect to A and second order with respect to B. Overall, it's a third order reaction. Again, we assumed all these reactions are elementary reactions. Unfortunately, very few chemical reactions are elementary reactions. Even this very simple chemical reaction between hydrogen and oxygen is not an elementary reaction. This is a very complex reaction mechanism that involves many elementary reactions. So let me show you. So when H2 reacts with O2, after ignition, the first step is H2 is decomposed into 2 hydrogen atoms. O2 is decomposed into 2 oxygen atoms. And then we have branching reactions. This H atom attack O2 to produce OH plus oxygen atom. H2 react with the oxygen atom to produce OH and a hydrogen atom. So again, those reactions are balanced. So now you see a bunch of OH being produced. And then this OH can react with water, react with hydrogen too, to produce water and a hydrogen atom. This hydrogen atom can be used to attack this O2 molecule. Again, there's going to be a collision between these two. Okay, and then the product is OH plus O. We have more O's. And this O can react with H2 to produce more OH. OH is very useful because OH can react with this hydrogen molecule to produce water, the final product, and another hydrogen atom. So this is actually propagation. It's a chain reaction. So now you can tell that even this reaction between hydrogen and oxygen is not a simple elementary reaction. It's a complex reaction mechanism. For those complex mechanisms, the coefficients tell us nothing about the order of the reaction. So when you look at this simple reaction, all right, over here, it's not a third order reaction. It's not second order with respect to hydrogen, and it's not first order with respect to O2. All right. So later, if you take physical chemistry, you'll learn that we can somehow come up with a much more complex rate law for this mechanism. All right. But for those mechanisms, how do we determine the order? Well, we can do this experimentally. Let me give you one example first. Just assume that the reaction rate is equal to the reaction rate constant K times the concentration of A to the power of N. So A is the reactant. So this is concentration of A to the power of N. N is the order with respect to A here. And then we can somehow measure the reaction rate with different concentrations of A. Okay, so we can use one concentration here. All right, it's A sub 1. We measure the reaction rate, R sub 1. And then we use a different concentration of A. Let's say it's A sub 2. And we'll get a different reaction rate, R sub 2. All right, so by looking at these two equations, you probably realize that if we do a division between these two, this K will disappear. Okay, we don't even need to know what the K is. So I'm going to use R1 divided by R2 here. Okay, you can do R2 divided by R1, same thing. All right, that will cancel this K. K disappears. And also, if you look at this fraction, A1 over A2 to the power of N, that will leave us only one variable to determine. That's N. Again, assuming we know the concentrations of A in the first experiment and the second experiment. Also, we know the reaction rate in the first experiment and second experiment. And then we can determine this N because in this equation, N is the only variable. But how do we do that? One way is to take the natural logarithm of both sides. So the natural logarithm of R1 over R2 is equal to, very simple, N times the logarithm of the ratio between A1 and A2. And therefore, this N is simple, the logarithm of the ratio of R divided by the logarithm of the ratio of the concentration of A. You need to be familiar with this logarithm. So the logarithm of A to the power of B is simply B times the logarithm of A. All right? And you don't have to use the natural logarithm. You can use base 10, you can use base 2, you can use any other base that's convenient for you. All right, for example, what if I just, maybe double the concentration of A? So this is 1 over 2. And I see the reaction rate is double. This is 1 over 2. And this time, I'd rather not to use the natural logarithm. I'd use log 2 because I know log 2 of 1 over 2 is negative 1. Here, log 2 of 1 over 2 is negative 1. And then I know n equals negative 1 over negative 1, and that's just 1. So that makes things a lot easier. All right, so again, generally we use natural logarithm, but if you find log 10 or log 2 more convenient, use those. All right, it doesn't matter. So again, you can use this. One more example. What if A1 is 10 times A2? Okay, I'm going to just use log 10. Log 10 of 10 is just 1. Let's say R1 is 100 times R2, and then we're talking about log 10 of 100, that's 2. Because 10 to the power of 2 is 100. And then we know n equals 2, because n equals 2 over 1. If R1 over R2 is 100, and A1 over A2 is 10. All right? So just whatever is more convenient for you, you can just use it. Log 10, log 2, natural logarithm, it doesn't matter. All right? And then how to determine the order of a reaction with multiple reactants. Let's say we have reactants A and reactant B. And then we just write out this R equals A times A to the K times A to the power of N and B to the power of M. And we'll have to determine the values of N and M. How do we tackle this problem? Well, we have two variables, and then the smart way is to hold one variable constant. We try to get rid of one of the two variables. So why don't we just hold the concentration of B constant, and then we can determine the reaction order with respect to A. All right, so now let's say we use the same concentrations for B in the two experiments. We only change the concentration of A. So we have A sub 1 and A sub 2 here. We measure the reaction rates, R sub 1 and R sub 2. And then we have this R1 over R2. And then it's going to be this guy divided by this guy. K on top cancels this K on the bottom. Also, B to the power of M on top cancels this B to the power of M on the bottom. Again, when we hold B constant. Now we have the simplified expression here. The result is A1 over A2 to the power of N. And then this N can be easily determined by taking the logarithm of the right-hand side and taking the logarithm of the left-hand side. So again, N is the logarithm of the ratio of R over the logarithm of the ratio of the concentrations. And then let's hold A constant. Let's focus on B. Make sure you use the same concentrations for A in the two experiments. You have a different concentration for B, B1 and B2. And then you measure the reaction rate R1 and R2. You do a division, and then R1 over R2 is simply B1 over B2 to the power of M. Therefore, M is simply the logarithm of the ratio of R divided by the logarithm of the ratio of the concentrations of B. All right? So now I'll give you another example problem. Let's say we have A and B as the reactants. We have some experimental data here. Those are my experimental data. We did this experiment 3 times. The first time I hold this concentration of B constant in the first and second trial. So look at these two numbers, they are the same. I doubled the concentration of A and the reaction rate doubled. So maybe we can just tell it's going to be just A to the power of 1. Very simple. And then let's compare these two rows. Okay, I hold the concentration of A constant and double the concentration of B. And this time, okay, these numbers are not very easy to analyze. The reaction rate increases from 0.2 to 0.283. So how do we tackle this problem? Well, let's get back to the first two rows just to show you the algorithm. N is just the logarithm of the ratio of R divided by the logarithm of the ratio of A, and then we have the ratio here of R. This is the ratio of A. The result is just 1. But again, you don't need a calculator. You can just tell the top is equal to the bottom. All right, and it's going to be easier if you use log 2. Okay, use a base of 2. But the last two rows are a little bit more complicated. So what you need to do is, again, you use the same algorithm. You plug in the numbers. This is R2, this is R1, this is B1, this is B2. And then you determine this M is actually 0.5. So this reaction is 0.5 order with respect to B, first order with respect to A. All right? The overall order is 1.5. All right? So we can also just just write it here. In this case, we can just copy and paste the equation here, and we can write it here. It's a to the power 1, we know that. It's b to the power of 0.5 after doing this calculation. All right. Now one more practice problem. Again, 3 data points. In the first 2 rows, we have a constant b. In the last 2 rows, we have a constant a. We do similar calculations, and all these numbers are exactly the same as the numbers in the previous table. I just changed this number to 0.4. And I just want you to pause here, think about it, maybe use a pencil to do the calculation yourself, and then I'm going to show you the answer. All right. So first, when we double a, look at this r. R is quadrupled, so actually r is proportional to a squared. And then now look at these 2 rows. When we double b, the reaction rate decreases. Okay, that's weird. Okay, you may find this is really weird. It does not happen for elementary reactions, but when you have a really complex reaction mechanism, sometimes when you increase the concentration of a reactant, actually the reaction rate may decrease. It's rare, but it may happen. All right, and then let's just use the algorithm. So this is the algorithm here. We take the logarithm of the ratio of r, the logarithm of the ratio of a. The result is 2. Again, r is proportional to a to the power of 2. And then use the last 2 rows. Again, the logarithm of the ratio of r, the logarithm of the ratio of b. The result is negative 0.5. So in this case, we're going to have a really interesting result. This is second order with respect to a, and negative 0.5 order with respect to b. And we know for sure it's not an elementary reaction. It's got to be a complex mechanism. All right.